Ever tried to clean up a messy calendar with overlapping meetings? Merge intervals is a pattern mastery 100 classic and a go-to at Google, Amazon, and Meta for interval manipulation and sorting skills. More than 30% of candidates miss subtle merge cases or get tangled in the logic. Master this, and you'll be set for any range, timeline, or schedule question. Let's break down merge intervals with the basic approach, so you can handle any overlap or merging scenario with confidence. Given an array of intervals where each interval is start, end, merge all overlapping intervals and return an array of the non-overlapping intervals that cover all the input. List of intervals, unsorted, may overlap. List of merged intervals, sorted, non-overlapping. Think of merging meeting times on a shared calendar so no one gets double booked. Interviewers might ask, how would you efficiently compress overlapping bookings or busy periods? What's tricky? Input intervals may be unordered. Overlaps may cascade. Merging two can create new overlaps. Sorting first is essential. Sort intervals by start time. Initialize a result list with the first interval. For each interval, if it overlaps with the last end result, start less than or equal to end. Merge, update end to max current end, new end. If it doesn't overlap, add it as a new interval to result. Let's clarify. Always compare current intervals start with last result intervals end. Only merge when there is overlap. Edge cases. Intervals already non-overlapping. All intervals overlap into one. Empty input. Sort intervals by their start value. Initialize the merged result with the first interval. For each interval from the second onwards. If interval.start less than equals last.end, merge, update last's end. Else, append interval to result. Return the result. Sort the list. Single pass through intervals for merging. Let's try to implement it using solution 1. This comment labels the strategy, sort the intervals, then merge overlaps. We start by defining the solution class. This defines the merge method, which takes a list of intervals and combines any that overlap. We sort all intervals by start time so they're in order. We create an empty list called merge to store the final intervals. We loop through each interval to decide if it starts a new block or should be merged. If merged is empty, or the current interval starts after the last one ends, we add it as a new interval. When there's no overlap, we simply append it. Otherwise, they overlap. We update the end to the maximum value to merge them. Finally, we return the list of clean, non-overlapping intervals. And that's how the algorithm works. Sort first, then scan once to merge anything that overlaps. Efficient and simple. Test input. These intervals show ranges on a timeline, with some overlapping. 1,3 and 2,6 overlap merge into 1,6 10 and 15,18 don't overlap keep as they are final expected. 1,6, 8,10, 15,18. Why the solution work steps. Sort intervals 1,3, 2,6, 8,10, 15,18. Scan and merge 1,3 plus 2,6, 1,6. No overlap with 8,10. Append no overlap with 15,18. Append final 1,6, 8,10, 15,18. Output matches expected. Now let's try another implement approach using solution 2. This comment says we're solving merge intervals using a stack-like structure. We define a solution class. This defines the merge method, which takes a list of intervals and merges any overlaps. We sort the intervals by start time so overlapping ones sit next to each other. We create an empty stack to store merged intervals. We loop through each sorted interval and decide if it starts a new block or merges with the last one. If the stack is empty or the current interval starts after the last one ends, there's no overlap. In that case, we push the current interval. Otherwise, they overlap. We merge them by updating the end of the top interval. After processing all intervals, we return the final merge stack. This approach sorts first, then merges using a simple stack, clean and efficient. Let's test our function using this input. These intervals represent ranges on a timeline, 1,4 and 4,5, touch, so they should be merged. 1,4 and 4,5 overlap/touch merge into 1,5 final expected intervals, 1,5. Why the solution works. Our algorithm. Sort intervals, 1,4, 4,5, loop through each interval. Push 1,4 onto the merge list. 4,5 overlap/touches, 1,4, merge to 1,5 final merged intervals, 1,5. The output matches the expected result. The algorithm efficiently merges overlapping or touching intervals into clean, non-overlapping ranges. Let's have a quick recap. We're given a list of intervals, and the task is to merge all overlapping ones so that the result is a set of sorted, non-overlapping intervals. Conceptually, this is all about organizing ranges, grouping overlapping segments so that each time span appears once. The tricky part is handling multiple overlaps that cascade. You can't just check pairs, merging one interval can extend into others. Sorting by start time is the key insight. Once sorted, you can scan linearly and merge as you go. It's clean, efficient, and easy to reason through. Here's the plan. Sort intervals by their start value. Initialize the result with the first interval. For each new interval, check if it overlaps with the last in the result. If yes, merge by extending the endpoint. If no, simply append it to the result. After one pass, you've got your merged list, sorted and clean. We followed that plan. Sorted the intervals, merged overlaps in a single pass, and built the final result step by step. The solution ran smoothly on LeetCode, no syntax issues, no logic errors. We verified the output thoroughly. Overlapping, adjacent, and empty cases all produced the right results. Every test case passed successfully on LeetCode. The key takeaway? Sorting simplifies complexity. By thinking in sequence and merging only when needed, you transform what looks like chaos into perfect order, one of the most fundamental problem-solving lessons in computer science.